every course instructor, teaching assistant, and any individual viewing this video. My name is Sudarshan Saraf. I am with my partner recording the video, Nilavra Ghosh. We're both second year electronics and communication majors here at IIIT Hyderabad. And for the spring 2025 course of electronic workshop 2, our project that we have chosen is an H-bridge motor driver circuit using MOSFET. So a motor, driving a motor is a big issue because there are different aspects, like we have to either the direction where we want the motor to run or the speed that we have to control it. So H-bridge fixes all that and encompasses everything into one. So using H-bridge we can control the speed, we can have bidirectional flow, and we have also included diodes, which we'll talk about later in the video, where we can even protect it from back EMF.
Our project, the total project consisted of 3 parts, where we were initially generating the PWM signal through the 555 timer, and through potentiometers we were varying the duty cycles of the PWM signal we are generating. After that, we had a gate driver which mainly does which is a high switching MOSFET, allowing us to give us efficient output through the PWM signal which we are generating, giving us input, and at the final we had a switch through which we were controlling the outputs A and B. The A and B were given as inputs to the H-bridge circuit over here, and this was a general overview of the circuit. Now we are finally going to explain the circuit in detail.
Why did we specifically choose PWM signal? So there's one thing that what the circuit, the H-bridge circuit sees on its face is a voltage, and if we send a pure analog voltage, there'll be a lot of power loss as heat, and the motor itself won't be able to overcome the torque using that voltage. So what we use is square waves, PWM waves specifically, and those waves are consequent on and off waves. So we accomplish this using a 555 timer and a potentiometer. So both of the roles of both of these in this is that why a 555 timer is better than just a potentiometer is that it helps in basically it has resistances in it, so that the power loss or the discharge in the timer itself doesn't cause power loss in heat. But if we simply use a potentiometer, there'll be a lot of power loss. So what we use here is, so these are the on and off waves, and there's a concept of duty cycle in this. So so basically what the face of the motor will see is an average of all of these waves. So, and we can control the duty cycle, or the duty cycle is the time when it's on, when the wave is at high, T high, and we can control the time that high is more than low using the potentiometer. So this is the formula that we use to calculate the duty cycle, which is basically the time mostly when it's high. And these are the formulas which we use to calculate pulse width, the time when it's low, the period of the whole thing. And here the RB is basically the potentiometer that we use. And for low, let's say here for low, we are only using RB. So we can say that the time when the 555 timer is low is only controlled by the potentiometer. And again, the formula for duty cycle. And yeah, that's how we show that 555 timer is basically a more efficient way of creating PWM signals to drive the circuit. For the second part of our whole circuit, we have a MOSFET driver. So for this, what our initial plan was to use a TC4427, but we only got TC4426. The only difference is that it's inverting, and TC4427 was non-inverting. So what this essentially does is, let's say we have a MOSFET, it needs a lot of power to drive it or to make it work. But the signal we're sending, like the PWM signal we're sending, are low powered. So this kind of acts as a middleman to balance that power gap, and gives power to the signal and increases voltage or current, whatever. So yeah, so that's what it is. Basically reduces the laziness of the signal, if you can call it that. And yeah, it's a game changer in in balancing the power levels. So we have also made an LP spice for it, which was So for the model here, we couldn't find any LT Spice model. We had to make our own model separately. So we found some online model which we implemented using this TC4426. This we added a block, and this SPTT switch is actually nowhere in LT Spice or nowhere you can find it. So this is essentially we made our own symbol in LT Spice to make this SPTT, and this is the code for it. So basically it turns it on and off based on whatever input wave, based on whatever is going in the plus side of the SPTT switch. This was the most difficult part in this. The IC we have used directly. So this driver is also followed up by SPTT switch. So these A and B we use the SPTT switch to make the signal go to either A or B. So these A or B control the bidirectional flow of the H bridge. So if it goes to A, let's say it is forward transmission. If it's B, then it's reverse. So yeah.
The LT Spice for the 555 timer was like the 555 timer module was used, where it was a circuit which we were implementing, and then came part for the potentiometer, which was like giving voltage of 12 volts and like having RA and R out based on that, and taking the voltage at a certain point, which was V out. And how was the potentiometer working? It was like we just gave a function for step param from like Rin going from some very low resistance to a very high resistance, and then the R out was which was minus of the total resistance and the Rn which you are giving, and the transient analysis were taking for 2 milliseconds. Then comes the H bridge part. For the H bridge part, the initial circuit was couldn't be implemented directly in the LT Spice. Thus, for that we converted from it to a mechanical circuit, to electrical circuit, and therefore it was implemented in such a way it was a main initial circuit. And after that, through the calculation, the formulas of electrical to mechanical circuit, and based on that the LT Spice was done. And how was the H bridge working? For the H bridge working, initially we had a circuit which was similar to this. This was then changed, and because of some issues which I'm gonna say now, because of the issues, like irrespective of having the gate driver, we were getting very small voltage inputs through A and B. Thus, for that, before the H bridges, we had a C amplifiers over here. So here we can see that the inputs are given through this input 1 and input 2, and after that the C amplifiers, based on that, takes it, like amplifies it with a certain amplification in, and then this was a PMOS, NMOS, PMOS and NMOS, which basically works like the PMOS. When we are getting low inputs, it's switching on while the NMOS is turning off. Similarly, the NMOS, when having a high input, was switching on and the PMOS was turning off. Based on that, when input was high through this and low through this, at that point in time, like the PMOS was switched on and the NMOS was switched on over here, since it was high over here and low over here. So it was the direction flow was the NMOS switched on over here, the motor driving over here, and similarly the low input to the PMOS over here. And the diodes over here are for the back EMF protection, which is very essential for a circuit. When the motors are switched off, at that time the back EMF comes into play, and thus for that the diodes are placed over here. Similarly, when it was low over here and high over here, after some amplification through here, over here, like if it's low, it's negligible. Then it was switched on over here and switched on over here, because it was high input over here and it was NMOS. So on, and the motor is running through forward direction, the other it was the backward direction. So this was our basic idea of a circuit. Now after this we are going to show the hardware part of the project we have done. So these were the materials required for a circuit, which are the basic materials required. Some were changed later on. Let's come to the hardware part. The hardware part, let me switch on the power supply for this. So this was the input. After the PWM signal, it is generated through the 555 timer, and through this we can see the duty cycle is being changed. Let me just find it a bit. So we can see the duty cycle is being changed when the potentiometer is being, like the resistance of the potentiometer is changed. Now the implementation of the hardware, like the motor driving. So the PWM signal is then, after the PWM signal is generated, is passed to the gate driver, and gate driver input. After that, after the gate driver, the inputs are given to the hedge bridge through the SPDT switch. The SPDT switch over here acts like, it's turned off right now. So we are like switching on it, and the motor runs very slowly because the potentiometer just current, that duty cycle is very low. So let me change the potentiometer. The speed of the motor changes proportionally. Let me just once again lower the duty cycle. Yeah, you can see the duty cycle is being lowered, and it's also been lowered. Now for the let me switch it off. At this point of time, the back EMF diodes comes into the point, and like it just protects it from the extra current that is flowing over here. And next, if the switch is turned opposite direction, the motor just turns on the backward direction. Let me change the duty cycle of this too. So we can see, as I'm changing the duty cycle, the speed of the motor is being changed. Similarly, you can see over there that the duty cycle is being changed. Similarly, the motor speed is being changed. Now let me once again just decrease the duty cycle, and we can see the motor gradually decreases the speed of it. So this was our main hardware implementation of the part, and through this we can say that through our project we can say that rather than just giving a direct motor control where we might find power losses and current losses, we have done comparatively a bit more efficient circuit. That's what our project is. Thank you.